can I have this in a different way? In other words, instead of having 1 6x6, 1 5x5, and 5 1x1s, can I have it as a different arrangement of squares? So those are the two questions, okay? And I think that maybe we can talk about this rather than using the whiteboard. We can talk about this for a couple minutes, maybe let's say 7 minutes. Let's talk about it in our tables. If, first of all, any rectangle can be decomposed, and if you believe so, then explain why. If you think that that's not true, explain why. And the second question is into how many ways we can make this decomposition. All right? Only integers, only using integers. And there is no further restriction on the integers. As long as they are positive integers, that's the only thing that we care about. All right? So let's think about this for 7 minutes. 7 minutes. And then I'm actually going to ask you guys to share about it. So again, 7 minutes starting right now. And then I'll ask you guys about it.
So I have a question about question number 2, where he's talking about how many different ways. Does that mean that you don't have to start with the largest square and keep putting in the largest square?
I think so, yeah. Because I think if you start with the largest square and you go to the next largest, you're only going to end up with one way to do that. So I was assuming he meant to do whatever squares you want. So you could do all 1x1s, and it would work.
Right.
For any rectangle, and then there'd be different combinations.
Mm-hmm.
That's what I understood. But yeah, he didn't answer your question.
So what's an argument of why we can always decompose it into squares?
Because you can always do 1x1, if nothing else. Would be my argument.
What about 1x1? What about the square 1x1?
Ooh.
If it's already a square, I decomposed it into one square.
So would the constraint have to be for all squares with n greater than 1? N being the side lengths.
Yes.
I'm just thinking, because we couldn't decompose a 1x1. That's the only condition in which we couldn't.
Is that where it gets to the session title?
Yeah, maybe. So yeah, you can say at least like the side length, at least one side length is greater than 1, because you could have a 1x2.
You should type that in the group chat, Jessica, so that we have it recorded. That's good stuff.
Okay.
And so then what about, as the rectangles get larger, can we see a pattern that forms to then create a formula?
So I think this fundamentally has to do with division, right? So like if you take that 14x6, 14 divided by 6 is 2 with some left over, which is really telling you that you can fit 2 6x6s and then have a 2x6 left. That 2 being the remainder. And since the remainder is always less than what you divided by, you know that you've sort of made this problem smaller in that sense, right? So what was the smaller side of 6 now is the larger side compared to that new rectangle that's 2x6. Does that make sense?
Yes.
I'm thinking of 14 as, can I type in here?
You can hit the T.
Yeah.
Oh, there we go. Let me make this bigger. I'm thinking of 14 as two 6s plus 2 left over. And that first 2 tells us we can fit 2 of those 6x6s. The 2 left over means we have 2 left as one dimension and 6, the old dimension, as now the longer of the 2 dimensions. So now we have to do this problem for a 2 by 6 rectangle. So then if we have a 2 by 6 rectangle, how many times does
So
2 by 6?
The 14 is a 6 by 14? Or it's a 2 by 14? Sorry, I missed that.
I was doing
So
the
the 14, it's a 2 by 14. Oh, it's a 6 by 14. Okay,
6 by
sorry,
14.
my bad.
The 2 times 6 means we can fit 2 6 by 6 squares next to one another.
Yeah.
And then we'll have, basically,
And then
what
you're
the
saying,
14 is 6 plus 6 plus 2.
okay.
Yeah, right. And then that 2 left over tells us a new dimension of just a smaller rectangle that we have to do the same game on. Right.
So you're saying it's kind of going to be like that recycling thing like we did in the first session? Okay.
So now, like, this rectangle over here is our new problem to solve. And it's a 2 by 6.
Yeah.
So how many 2s fit into 6? Well, 3. And then we're done because we got a remainder of 0. I don't know if this is answering his questions, but I thought it was a cool connection to division.
Yeah, it's still a cool thing to see and discover. Like,
My
thinking about
internet's-
it.
So the first question was, is there any rectangle that we cannot decompose? And that would be the 1 by 1. What was the second question?
Is how many ways we could do it.
Right. So definitely, you know, once you have it segmented into the least number of squares, which we've done, you can take any one of those squares and make it smaller squares.
Yeah.
But how many different ways there are, I'm not sure how to tackle that.
Yeah. Well, I guess would it depend on like the difference of the dimensions, or would it depend on the divisibility of the dimensions? Kind of like what you got into here. Like when you do 14 divided by 6, you get 2 in a remainder. Would that affect the number of ways that it could be done?
Well,
So if we take this 14 by 6.
Yeah. First, I'm just curious, is there a way, if I say a 6 by 14, can you immediately say the least number of squares, in this case would be 5, right?
Mm-hmm.
We have a 6 by 6, a 6 by 6, and 3 2 by 2s. Could you know that beforehand? Like you give me two numbers and I immediately say how many minimal squares. Because I think once we have that, then we can chop those big squares into smaller squares.
Yeah. Well, I mean, you did the 14 divided by 6, and you got 2 with a remainder of 2, and then you take the 6 and you divide it by 2 and you get 3, and then you added those together. Like, would that kind of thing work no matter what? Like, and if there was another remainder, you would just have to do it again.
Yeah, right. Exactly. So like the 13 by 7 was a good example where you have to do this 3 times over. Because 13 was 1 7 plus 6 left. And 7 was 1 6 plus 1 left. And then 6 was 6 1s plus none left. There you had to drill down to 1 by 1s.
Yeah.
It's interesting how the least amount you can see with remainders and divisibility.
Yeah, I think I have I'm going to change the order of this. I'd rather this be a how do I edit that? Yeah, if we just keep doing this division, I think our least number of squares is just adding up this column. So 1 plus 1 plus 6 is 8. 2 plus 3 is 5.
Yeah. That's a cleaner way to look at it than what I was writing on my paper.
But could we know that without doing the whole calculation? Like if I said a 15 by 37 or something, could you just say, oh, that'll take 6 squares? Minimal 6 squares.
All right. Let's see what you guys found so far. 2 questions, right? 2 questions. Can we always do this? And the second question is if there are multiple ways of doing that. Sure, I think I can broadcast the message, Stephen. Yeah, thanks for that. So yes, next time I'll send a broadcast, like a warning that I'm going to take over, if that's okay with you guys. So if anybody wants to share their findings, that would be good. Maybe I would ask for a volunteer, so it's not like a weird monologue. If somebody wants to come and present with me, let's see if this works. Please let me know. And I guess we can all hear from them for a couple minutes to see what they found. Does anybody want to try this out? If not, it's okay. I can just read your comments, whatever you guys prefer. But again, if somebody really wants to jump in and talk a little bit about your findings, just let me know, okay? Remember, the 2 questions were if we can always break these rectangles into squares, and if there is a unique way of doing this. Maybe we can start with the first question, like just a simple poll, yes or no question. Do you think that this is always possible? What do you guys think? Is this always possible? Yeah, I think it's always possible. Yeah. And more than that, I know that it's always possible. And Stephen, yeah, that's a great point, that the ratio is a rational number, right? We are restricting ourselves to integers. So later, in a couple of minutes, we will see what happens when we allow for irrational numbers. So yes, we can always do this. Now, the second question about uniqueness, I think a lot of you guys hit the spot over there where you were considering if you can alter or you can change the rules. Fan, do you have a question or you want to say something? The rule about, I guess the rule that I'm talking about is starting with the biggest square that you can fit first. So if you remember, let me again go back to the whiteboard. Yeah, we need to use the biggest one first. But I was kind of subtle with the position where the way that I would locate this square, right? Because I actually drew it here in the corner on the left-hand side, but that was not really an explicit rule, right? I mean, really, I could have drawn this thing anywhere. So what I'm trying to say is that this square right here, I could have drawn it like in the middle, or maybe to the right-hand side, or maybe not exactly in the middle, but somewhere in between. And the question is, if I do that, if I have this square drawn maybe in the middle of my 11 by 6 if I would still get the same decomposition. In other words, if I write down this guy in the middle, say instead of having the 5 on one side, I actually end up with the 3 and the 2, right? That's really what I'm thinking about. Would I get a different decomposition? Well, let's try to look at in this case. I guess if I try to do the decomposition in here, and please correct me if I'm wrong, but I would get a 3 by 3 in here, and I would get another 3 by 3. And here, I think I would get 3 2 by 2s, right? So even if I keep that rule of trying to fit the biggest square in any empty space, if I don't have a rule about the position, where should I put that thing, then the decomposition I don't think is unique. Do you guys see my point? If I don't make the restriction or where can I put this square, then the decomposition would definitely not be unique, right? Ernest, all rotations and reflections also could make a difference, right? So hopefully you can agree with me that we have to make the rules a little bit more precise. Okay, so whenever we're talking about this decomposition into squares, I want to be a little bit more precise on the rules. So what I want to fix on is basically, one, that we want to fit the biggest squares, and two, we're going to follow a specific order. We're going to start putting our squares following a spiral. So let me try to explain what do I mean by that. So I want to start fitting my squares in some sense like a spiral. So let me do another example in here. Let's see. Let's do a, if you guys want, let's do this other rectangle. And suppose that this is going to be a 12 by 5. Okay, a 12 by 5. So what I mean in here by following a spiral is, first, I want to stack all my rectangles from left to right. Again, we're talking about the topologies rectangles, right? Squares. So I can fit 2 of these over here, and I'm going to start fitting them from left to right. Now, from the remainder, I have 2 by 5. I have a 2 by 5 rectangle. I want to start fitting them from top to bottom. So I can fit 2 of these, right? I can fit 2 of these. So I have a 2 by 2, and I have another 2 by 2. And I end up with a 2 by 1, right? And now I want to fit them from right to left. Do you see how my arrows are following a spiral? That's what I mean with the positioning. In other words, I would have a 1 by 1 in here, 1 by 1, and I would have another 1 by 1 in here. Okay? So in other words, the way I want to position my squares is going to follow this spiral thing. And this is going to be a clockwise spiral. So I want to fit my rectangles from left to right, top to bottom, right to left, bottom to top, left to right, top to bottom, and so on. Okay? Does that make sense so far? So we're following this spiral in a clockwise direction. And whenever we fix those things, we have one, that the decomposition exists. It always exists. We can always do it. And number 2, we can do it in a unique way. Okay? Those are the 2 things that will happen over here. So let's see. Let me just do another example. Yeah, Chris, I think that actually you had the main idea before. because you said, I believe you said that this kind of reminded you of the division algorithm. And that's what we're going to explore in a second. So, for example, let's try to do another one. Can anybody suggest me two numbers? Can you guys tell me two numbers? So we can try to explore another rectangle. It doesn't matter, whatever you like. I guess if they are not mutually prime would be better. Maybe if they have a common divisor would be a little bit more interesting. And you will see in a minute why it will be more interesting. So let's do 6 and 15. Let's do, Nanette, 6 and 15. And I chose those because they are not perfectly divisible by each other. I think that will be very important for us. So 6 and 15. I guess by the end of this session, I'm going to be great at using my Wacom tablet. Or at least I hope so. So we have this, and again, remember the process. Let me try to make it a little bit nicer this time. Let me try to use some colors. So the first one, I can fit two of these, right? I can fit two 6x6 over here. So let me just write how many of the squares I'm able to fit. So my first stage is going to be two 6x6. The next one, let's see, how many can I fit in here? I have then 3 and 6. That's the remaining one, right? So I can fit 3 of these. So I have, not 3, 2. I have 2 of these guys over here. So I have these 2 guys. So I have 2 3x3 squares. Okay. Now this is pretty interesting because the smallest square that I have in here, the dimension or the size, I would say the length of the smallest square is a 3. Now the question is, what's the relationship between 15, 6, and 3? Do you notice anything with that? So Chris is suggesting that 3 is the GCD of these two things, right? The greatest common divisor or the greatest common factor. And the question that arises then to my mind is if this is always the case. If this is always the case. If whenever we start with 2 numbers, the size of the smaller square will be the GCD. Does that make sense? Question is, if all the time, whenever we start with 2 numbers, the smallest square, the one that we end up with, is always the GCD. That's a question that pops into my head, okay? So I think that one way that we can explore this, one way that we can try to see if we can answer that question is the following thing. We were trying to, given a rectangle, to find the decomposition. So what I'm going to give you now is I would say the opposite task. So I'm going to give you the decomposition, and the task is to find the rectangle, the original rectangle. But I'm going to make it a little bit more interesting. So remember how we used to count the number of squares and the sizes of those squares? Now I'm just going to give you the the number of squares and the size of the last one. So in here, for example, I'm going to tell you that there are 4 2x2s. That is this is the last stage. Then on the previous stage, we had just one square, but I'm not going to tell you what was the size of that last square. In the previous one, we had 3, and in the first stage, we had 2, but the sizes are unknown. So the task for you guys right now is trying to see if you can reverse the process. In other words, I'm giving you the last stage, but I'm not giving you what is the size of the first stage or the second stage or the third stage. I'm basically asking you to draw the diagram for me, okay? So let's actually fix on this one that I wrote in here. I know that in the first stage, there are 2 squares. On the second stage, there are 3 squares. On the in the third stage, there is only 1. And on the last stage, there are 4. And those 4 actually have a size of 2 by 2. So the task is to find all the previous stages. Does that make sense? Is the question clear for everyone? Maybe we can think about this for, I would say, some 5 minutes, 5 to 10 minutes. Everybody agrees with that one? Yeah. I can type in the chat. Yes, let me type it over here. So basically, the first stage was 2. The second stage was, the second stage was 3. The next stage was 1. And the last stage was 4 2 by 2s. Okay, so I just typed it on the chat so everyone can see it. Again, the only sizes that I'm giving you is the last stage, the very small one. All right. So the question is, can you find the sizes of all the previous stages? Okay, so I'm going to give you again. If you want, let's work on this for, I would say, 8 minutes. And then we can see if you guys can find it. And I'll try to remember to give you a warning before I go into presentation mode. All right. So again, you can ask questions all the time. And also one thing that I wanted to mention is that you are allowed to switch tables. That's one of the nice things about Remo, that you can switch tables. Okay. So if you're on your own, please feel free to join another table. And I'll see you in a couple minutes. All right. So did you guys find the Euclidean algorithm? Yeah. So let's see. I think, or at least I've heard a couple people agree with Chris with the sizes. That means that that our rectangle was originally an 86 by 38. So just to be clear on that, let me again go back to the whiteboard and see what happens over here. Let me just do a quick run of how we can find this. But again, in the end, it's just the division algorithm backwards. That's basically what it is about. Okay. So let me try to move into an empty area. And if you remember, we said that we were starting with 4 2 by 2s, right? That was my starting point. 4 2 by 2s. My handwriting is getting worse. All right. So what does that mean? Well, it means that I will stack, or I will put the 4 2 by 2s next to each other. And by the way, it doesn't really matter if I start with them horizontally or vertically, right? Because in the end, the only difference will be that the rectangle will be rotated or not. So I think that it's safe to assume that I can start with them this way. Now that means, that means that that my tablet is being crazy right now. There you go. Okay. So I have my last step over here. And now that means that the previous step, I had squares that will be on top of these ones, right? And I had one square, just a single square of these. So I think that I can safely say that I have one square that is given to me by the number of the previous squares, right? So I had 4 of these, the number of the previous squares, but each of these was a 2 by 2, right? So actually, this will mean that these guys should be 8 by 8. I have 4 2 by 2s, and that will give me one 8 by 8. So in the end, this guy right here should be an 8 by 8. So what I'm trying to say is that in the end, the previous one would be 4 times 2. The number of squares times the side of the squares. So this is the size that I have in here. The previous one would be that, right? And now I have just one of these, which means that my next square that is going to be next to it, you see that it will be the previous stage plus the previous one. So actually, this thing should be not only the one square that I have of size 8, but actually the previous stage. So this really resembles the Euclidean algorithm, the division algorithm, because this thing right here is counting how many of them. This is basically the quotient. This one right here, this is the divisor, which is the size of the previous step. And the size of 2 steps before that, that is the remainder. Hopefully you agree with what I'm doing over here. So that means that my previous step should be a 10 by 10. But I actually have, how many of these I had? I have 3 of them, right? So I have 3 of these 3 by 3s. Sorry, 10 by 10s, not 3 by 3s. And then the next step would be this big guy right here, which if I follow that Euclidean algorithm, that means that I have 3 of the 10 by 10s. So again, the number of rectangles times the size of the rectangle plus the remainder, which was the size of the previous stage, right? And this will give me the 38 that Chris was sharing with us. Okay, so that will be that one. And then the last stage, this is getting really big. Then I would have 2 of them. And again, if you look at the equations, you can definitely see the pattern is the number of squares times the size of the previous stage plus the size of 2 stages before. So this will give me, that would be what, 76, 86. And I think that's what Chris was sharing with everyone, right? Let's see, does that mean? Oh, we have an announcement. The event has extended for 30 minutes. Oh, because we are about to finish, right? Okay, so I'll try to hurry a little bit over here. But hopefully that makes sense, right? And if we read this from bottom to top, if I read it this way, this is just the division algorithm. This is a visual representation of the division algorithm. Now, if I can do the division algorithm in this way, that means that all I'm doing is working with fractions. And this is precisely what I wanted to share with you guys, that this is a visual way of working with fractions. And in particular, hopefully you can see it over here. I'm trying to describe this fraction, 86 over 38. Because if I'm reading my division algorithm, this should mean that this is 2 plus 10 over 38. Hopefully you agree with me. This is just a different way of writing down that division algorithm. And of course, secretly, I'm going to write it next to this guy. I can actually simplify this expression because this thing should be, what, 43 divided by, I believe it's 19, right? If I divide by the greatest common divisor, oops, sorry, not that one, but this one. If I divide by the greatest common divisor, I have that fraction secretly is the same thing as 43 over 19. I think maybe that's what Fan was finding, which is pretty much the same thing, okay? Now, this is the cool part over here, because I can do a trick, and I can write down the second fraction. Let me know if you can see that over there. But I can write down that second fraction as 38 over 10. Okay, and you might say, like, why would I want to do that? Well, I just want to do it that way because I like to make my life more complicated. But actually, that second fraction, that 38 over 10, that comes from the second division algorithm expression that we did. That actually is going to be 3 plus 8 divided by 10. Again, another use of the division algorithm right there. So notice how I am decomposing this fraction into a weird way, right? This weird way actually is what we call a continued fraction expansion. Now I can keep doing this thing again, and I'll have 2 plus 1 over 3 plus 1 over 10 over 8. Oops, that's a pretty bad 10 over 8. And I can use the division algorithm one more time, because that would give me, let's see if I can fit it over here. That would be the same thing as writing down 2 plus 1 over 3 plus 1 over 1 plus, what would be the last one? That would be, if I'm reading my previous part, that would be 10 equals 1/8 over 2. So I would have a remainder of 2 over 8. So that would be, if I can fit it over here, 2 divided by 8. And then this would be the same as writing down 2 plus 1 over 3 plus 1 over 1 plus 1 over 4. And these numbers were the ones that we had originally. Right? I don't know why the whiteboard went away. I'm sorry about that. But basically, the number of squares are going to be those coefficients over there. Okay? And those coefficients right there are the ones that we call a continued fraction. So basically, the continued fraction that I'm talking about is going to be 2, 3, 1, and 4. And this one, I'm just going to write it down over here. Usually we denote that by using brackets, 2, 3. I don't know why the thing is going away. So let me just type it here on the chat. I'm sorry about that. So 2, 3, 1, 4. Okay? So this is a visual representation. This is a really handy notation of this square decomposition and this fraction decomposition. Okay? So hopefully that makes sense. And the nice thing, and let me try to finish with these ideas, is that you can decompose any fraction, as we showed, by doing this rectangular decomposition into squares, and you can write it down as this continued fraction expansion. So in here, the first number is going to be like the integer part, and notice how the next coefficients are going to be different, right? I use the semicolon after the first one to indicate that the first one is the integer part. So, for example, we were doing 86 divided by 39. No, 36, I'm sorry. No, 38, right? And we denote that as 2, semicolon, 3, 1, 4. Which means that I can write down this fraction as that continued fraction. And then you might ask me, why would I want to go into this trouble, right? I mean, why do I want to make it more complicated? Well, one of the very nice applications of this, I always leave the most interesting thing to the end, is that I can approximate things if I truncate this continued fraction. In other words, if I would like to approximate the fraction 86 over 38, I can approximate that with just 2, 3, 1, for example. So what would that be? Well, that would be 2 plus 1 over 3 plus 1 over 1. Yeah, hopefully I got that right. And notice that this is a smaller fraction. And can I work out that fraction? Yeah, I can work out, even I can work out that fraction. That will be 1 plus 1/4. Am I right? Please, if you can double check my math, because I'm terrible at that. But this will be that fraction can be approximated by 2.25. Again, please, if you can double check that for me, that'll be awesome, right? And if I actually grab a calculator, or as we call it nowadays, cell phone, the original fraction we started with, let's see, what is this going to be? This is 86 divided by 38. That's 2.26, 31, which is very, very similar. Yeah, Chris, it's very similar, right? So all this nonsense actually has a nice application. You can approximate things. You can approximate fractions in a very simple way, right? And then going back to some of your original questions, if we can do this with fractions, we could also do this with irrational numbers, not only with rational numbers. So for example, let me just cheat a little bit, because I like to cheat, but let me write down the continued fraction decomposition for pi. Because actually we can do this for any number that we want. Any real number can have a continued fraction decomposition. And again, I'm cheating in here, but for the purpose of this demonstration, we allow cheating. So the continued fraction decomposition for pi, I'm just writing down the first decimal places, is going to be given by 3, 7, 1, 1, 1, and so on. So this means that I can approximate pi with fractions in a very efficient way. The first approximation that I can make to pi is, of course, just getting the first number, which is 3. So, of course, pi is approximated by 3. Okay? Not really deep, but it's okay. But the next approximation, I think it will be a little bit better, because this is telling me that the next approximation is 3 plus 1 over 7. And 3 plus 1 over 7, that is a little bit better. That's the 22 over 7. That is kind of like a famous approximation of pi. But even I can take this a little bit further. Well, if we want, let's compute the 22 over 7. That is 3.1428. It's pretty decent. And for my last magic trick, the next one, which would be 3, 7, and then 15, this should be a little bit better, right? This should be 3 plus 1 over 7 plus 1 over 15. And with this one, I probably would need a little bit more help from you guys, because I'm not that good. This approximation would be then, what is this? this is going to be, I'm trying to write down the fraction in here. Is that right, Stephen? 333 over 106? Yeah, and I have the decimal for this one. And that's way more accurate. Only with two continued fraction places. So this is pretty cool because with that very simple rectangle breaking into squares, I can actually come up with very, very good approximations of pi, if that makes sense. So let me just wrap it up because I don't want to go over a lot of time. Even if we started a little bit late, I want to finish on time. Somebody mentioned something about Fibonacci numbers. Like the Fibonacci numbers, if the ratios of the rectangles were Fibonacci numbers, then that would basically give you the longest chain of squares, something like that. And that's because if you write down the continued fraction for the golden ratio, you can look this up in the internet if you want. The continued fraction for the golden ratio, it's very special. It's a very special continued fraction because it's given by this. This is the continued fraction for that, where everything is a 1. So you probably have seen the golden spiral where you actually take a rectangle with 1 and phi as the dimensions, and then you start breaking these things into squares. Then you join all the tips or the edges of those squares and you get the golden spiral, the Fibonacci spiral. That's exactly what we're doing. But instead of being just a finite number of stages, we have an infinite number of stages. Okay? And it happens to be that whenever we compute the fractions, like, for example, 1 or 1 and 1, which will be the next one, or 1 and 1 and 1, and so on. Really, what you end up with, if you want to compute those things, are just ratios of Fibonacci numbers. Something like that, which is pretty neat. In other words, when you take ratios of Fibonacci numbers, that is going to give you the best approximations to phi, to the golden ratio, which is pretty much insane because all comes just from this very simple, very naive way of breaking rectangles into pieces. Okay, so hopefully you enjoyed this session. At least to me, it was pretty fast. Actually, I thought that the hour and a half was going to be like forever, but I really enjoy this this activity, and it's definitely very approachable if you want to work it with your students or even for your own. I mean, I really like discovering these things. I'm just going to leave you with one website that I found while preparing for this session that has a very nice online calculator where it will do the decomposition for you. So if you want to dig a little bit deeper into that, I shared the link here in the chat. Go ahead and check it out. It has way more information about continued fraction and how to do approximations. I think it's a very nice topic. So thanks again for being here for like the long day. Hopefully you enjoy it, and hopefully you will keep coming to the sessions the following days. Just let me know if you have any questions. I'm sure that you can find my email with the organizers. And thanks again for this wonderful chance to present with everyone. So don't forget of filling out the survey whenever you have time. And I don't know if we're free to go. If somebody else wants to speak, if anybody has a poem, a joke, or a song, I don't know. But again, thanks for being here. And stay safe, everyone. Use masks. Try not to go outside too much. And hopefully you enjoy the other sessions. Okay. So thank you so much. And I think we'll see each other soon.